Bismillahirrahmanirrahim. This is the second video of the Adaptive Control course as offered at the Faculty of Engineering in Cairo University. Uh, First, I will give an overview of the course contents, then I will start our first topic on parameter estimation. The first topic in this course is on real-time parameter estimation. The estimated parameters are then used to design a deterministic discrete time self-tuning regulator using a pole placement technique, and this would be our second topic. The third topic assumes stochastic discrete time models and looks at the design of an adaptive predictive controller. So we'll start by minimum variance control and we'll go through it till we reach the generalized predictive controllers. The fourth topic on model reference adaptive systems, and this will be in continuous time. Finally, we will have some selected adaptive controllers. Hopefully that will include adaptive fuzzy controllers, backstepping adaptive controllers, and L1 adaptive controllers. So let's start our first topic on parameter estimation. The final objective is to have a recursive technique to calculate the system or the controller parameters, and that will be online and in real time. The basic algorithm is based on the least squares principles. However, to give an overview and a comprehensive understanding of the problem, we'll start by talking about the system identification problem as a big problem, and then go down to the parameter estimation part. So in system identification, we assume that we do not know the model. So to derive a model that corresponds to a real system, we could have different alternatives. First could be based on the physics, which means that we use the principle of say in electrical systems, principles like Faraday's law, Ohm's law, Kirchhoff's laws, and so on. In mechanical systems, you could use Newton's laws. In thermal systems, you could use the principle of energy of conservation, and so on. So this could be one way to derive a model. Another way is to depend on experimental data. And of course, we could have a combination of both physical laws and experimental data to come up with a good model. Now, if we decide to use experiments, then the planning of the experiment will include the signals to be measured, and most importantly, it will include the type of input that we should apply at the system, so that the output of the system and the measured signals will expose the different dynamics of the system. This problem is called in system identification, parameter estimation, and adaptive control persistent excitation conditions, the conditions that the input must satisfy in order to be capable of identifying correctly the unknown system. We also have to select the structure of the model, whether we would like to have our model in the form of a transfer function or impulse response or state space models. Then the next step would be to implement an algorithm to estimate or to calculate the unknown parameters of the system. In our course here, we are going to focus on recursive least squares as a basic technique, and its variations, of course, as a basic technique for parameter estimation. Once we have a model form and parameter values, then the next step would be to validate that model by comparing its output with the output of a true system. If this is satisfactory, then we take that parameter estimation and model as representations for the system, and we depend on them in control design. But if not, then we have to redesign our experiment in order to get a better model that fits the data. There are two basic techniques in system identification. One which depends on non-parametric methods, and that will include frequency response analysis, transient response analysis, and we have all seen frequency response analysis in body plots, for example, where we can plot the magnitude and phase versus frequency, and from that we can conclude the corner frequencies and the gain of the system, and correspondingly we can deduce the transfer function of the system. We can similarly, by having a transient response of the system, we can conclude the transfer function of the system. However, that technique is maybe limited to low order systems. In stochastic systems, we could use correlation analysis and spectrum analysis. The other main technique in system identification is the parametric methods, and that includes the least squares and maximum likelihood. Finally, an important topic in system identification is related to model reduction. We all know that real systems should be represented by high order models. However, we normally can neglect fast dynamics or non-dominant poles and so on to reduce the model order and make design easier. The procedure to correctly reduce the order of the model is studied under the topic model reduction. A good reference, actually the main reference in system identification, is a book by Liang, and it's called System Identification Theory for the User.